Nice.
All right. Okay. Should be good.
Thank you. Okay. Don't know if I'm audible enough. Is it? Okay. Thank you. Hi, everyone. Thanks for coming today. I'm Tanmayi, and I'm going to show you a very brief introduction to zero-knowledge proofs. So we're barely scratching the surface. We're not worried too much about mathematical proofs or too much into the detail of it, because that's like a whole class. It's a whole course, right? So thank you, blockchain, World of Blockchain, and Taghi for the wonderful opportunity. So let's get started. Okay. Oh, so before that, a bit about me. Like Taghi introduced, I'm a master's candidate in applied science, ACE, and I'm working with ZK digital signatures that are post-quantum secure. So it's not zero-knowledge proofs in general. It's a very it's a narrowed down scope of just to like the quantum post-quantum secure algorithms. And I was a software engineer before this in India, and I was working with telecommunication protocols, but now I'm here, and I also love poetry, and I'm into literature and dance. So this is my LinkedIn QR, so you can also just type in my name, and I would love to connect with all of you. I'm pretty sure you're all blockchain enthusiasts, and I would love to make new connections in that area. So moving on. So to begin with, I just want to introduce you to why would we really need zero-knowledge proofs, right? So imagine there's a massive healthcare hospital or a healthcare center, and it uses blockchain to store all of its data and to manage patient transactions, right? So each of the blockchain transactions contains, because it's on the public ledger, it'll have probably when I say hashed, it's like a pseudo-anonymized patient name, and it would have, say, a date of admission, the insurance number of the patient, and their medical history, perhaps, right? And so there's this one, imagine that an adversary does have they have, of course, everybody has an idea of what the ledger looks like, but imagine an adversary can actually query it. So we have Alice, who is a patient at the hospital, and she goes on to Instagram. Like she's like all of us. She just goes on Instagram, and on the day of admission, and she's like, I'm getting a surgery. I'm at the hospital, and I'm sick, right? So what happens here is an adversary can potentially look at the date posted of Alice's post, and also try to match it with the date of admission that is available on the public chain, and potentially try to narrow down. There might be a lot of patients being admitted that day, but that's still a form of delinking, right? So the anonymity of Alice is not really withstanding in this scenario, because maybe following a few other a few other social engineering attacks, the adversary can probably narrow down that this is probably the medical insurance and history of Alice, right? So he can trace it back to Alice. So this is a potential problem, because this also means that there is insufficient consent, which means that the patients that might consent to data sharing do not realize that this information is actually permanently visible to anyone who has access to the blockchain. So the patients may not fully understand the implications of having that, and they might consent to data sharing without realizing this, right? And once the data is on the blockchain, it cannot be altered or deleted, and the patients who are consenting to have their data stored in these blockchains might not know that. And there's also linkage attacks, like we just talked about, where an adversary could link seemingly unrelated data points across all transactions to external databases to potentially de-anonymize, which means to get a link to the owner of a certain transaction, right? So which essentially means that transaction patterns can reveal identities. And this is a problem, because the result is stigma and discrimination and so many other worse things that we cannot sit down and imagine at this point unless the attack actually happens. So how we can fix that is this would be a great motivation to apply zero knowledge proofs. So we can start to look at what zero knowledge proofs are, and maybe there's a way we can establish how we can solve this problem with zero knowledge proofs, right? So, So the agenda for today is I'll be giving you a brief introduction to ZKP. So we'll look at some basic construction of proofs, and I'll also tell you a bit about what proof of knowledge means, and also a very, very basic introduction to ZK snarks. Please remember that I cannot show you the mathematics of this right now because that's well beyond the scope of this talk, but we will still talk about what they are and how they're used in the industry or in the what the research is right now. And we'll also look at Zcash, which is a direct zero knowledge implementation on the blockchain, and current current research in the areas, right? So I want to make this as interactive as possible in the sense that I have tried to include as less math definitions as I can, so in order to not have you bored, right? So now we'll start to provide a brief intro to ZKPs. I'll touch on what a proof is and what does it mean for a proof to be zero knowledge. Okay, so if you look at the screen, suppose look at the first statement here, and this is what we called a classical proof. So suppose there is a statement which says that n is a product of two primes, p and q. And they're large primes, which means that factorizing them is not really possible as a human being or even for a normal computer, right, in polynomial time. So this is a prover and a verifier that we introduced. And so there's this claim that is public, that is known both to the prover and the verifier. Now, for example, the claim to this is that the prover knows the prime factors of n. So the prover says to the verifier, hey, I know the prime factors of n, and the verifier's job is to prove that, is to verify that the prover really does know that information, right? So this is how it works. So the claim is publicly available to both the prover and the verifier, and the prover computes a proof and sends it to the verifier, who verifies it and outputs either a 1 or a 0, indicating an accept if the verifier is convinced that the prover really knows the information or the proof is correct, and a 0 if to reject the proof. So how can a prover really convince the verifier of the claim? So would you have any idea right here what the prover can give the verifier so as to convince them of the claim? What parameters do you think would the prover share to the verifier? That's okay, we can look at the answer. So she puts the prime factors p and q in the proof, right? So unless the verifier in this scenario looks at the fact that the prover has p and q, he will not believe her. He will not think that she would have the factors of p and q. So in this proof, especially for this claim, the prover is sending all of the information, which is p and q, and n is already known. So really, that's all the information there is, and it's just showing that, okay, I have this, and the witness is the fact that I have it. I'll just show it to you, right? So we'll also build on what an efficiently verifiable proof is, because it's important that in computer science, all of this computation happens in polynomial time, right? So it means that the prover doesn't have all the time in the world. The prover has a limited time, which is the polynomial time, and I said prover, but I meant the verifier. The verifier doesn't have all the time in the world. They just have a polynomial time to verify the proof. I'm sorry about that. Yeah, so this proof is an NP proof, which is efficiently verifiable. It means that the prover works really hard to make the proof short so that the verifier doesn't spend years of time to verify it. So this is just, you don't have to really think too much into it, but just to build context, when I say polynomial time, it's the polynomial it's polynomial in the size of the claim. So here x is the length of the claim. If you imagine the claim is like a string, so the w here is a witness. So the proof will be a witness that is polynomial in the length of the claim that the verifier can verify in polynomial time, right? So this is the official, I don't know if it's official, but it's like the mathematical definition of what this proof is, and it has been borrowed from this really nice ZKB MOOC lectures that I recommend all of you to check, because so I'm just a messenger, right? So whatever I'm presenting right now is a lot of content is borrowed from there. So it says that L is an NP language. Then if there is a polynomial if there's a polynomial length of x time verifier v, where there is completeness, which means the true claims have to be short. So two claims have short proofs, which means that there is a polynomially x long witness w, such that the verifier that runs the algorithm x and w outputs a 1. Another property of this is soundness, which means that false theorems have no proofs. So there is no way that the prover can provide a witness if it doesn't actually exist in the language. So we can probably go over that in a bit, as in if you're a little dazed about that, we can try to circle back in some time. But we can move on for now. There's another way of making this proof work, right? So right now we discussed that the proof had both of the prime factors, P and Q, given to the verifier, which means there is no new information. So given this, is there a way that such a prover does not have to give out P and Q? Right, so we have to think about ways in which we have to make this of some benefit, because otherwise what is the point of all of this? Like, why are we doing the proof if we have to provide the whole proof? Then there is probably no efficient way of doing this, right? So there is a way, and information theorists and computer scientists in 1989, they wrote a paper. This is Shafi Goldwasser and Micheli and Rakoff, who wrote a phenomenal paper that proves to be the fundamental of zero-knowledge proofs as we know it. They said that it is in fact possible to send the proof without showing the verifier of the information that the proof is made of, right? So it basically lies in the intuition that the prover says, I could prove something if I felt like it. And the verifier just says that you would need to convince me of that fact, and then every time you try to prove something, I will believe you. But first you would have to convince me, right? So at the end of this whole protocol, the verifier does not learn the NP proof itself. So he will still be able to accept the proof without learning anything about what is actually in the proof. So these are the two properties of zero knowledge, proof of knowledge, which I think is in most textbooks. The first thing is there is an interaction, right? So the prover and verifier engage in non-trivial interaction, and there is randomness, which means the verifier runs a randomness parameter. Usually he just flips a coin so that the prover does not anticipate the questions that the verifier asks them. So that's the whole point of the randomness. And it also means that there can be an erroneous accept or reject with a very small probability. But it's like 1 in the order of like 2 power lambda, where lambda is like the security property of the protocol. So it really doesn't matter. If it's really, really small, you can still accept it, right? So let's get into an example which is not mathematical. So I tried to make sense. I'll try to make sense of this, and you let me know if it really makes sense at all, because right now it seems pretty crazy. How can you just present a proof without showing the verifier what is in the proof, right? So here we have a piggy bank, which is just a toy where a lot of coins that you save, and the prover is in pink. So now the prover says, I know how many coins are in the piggy bank, which means the prover is able to count, right? It has the ability to do that. So, and then the verifier would say that the verifier then flips a coin to decide whether to add a coin or to do nothing. So the way that the verifier decides to prove this is he would say, okay, let me flip a coin. If it lands on heads, then I will add a coin, and if it lands on tails, I will do nothing, right? So then the coin flip eventually in this scenario results in heads. So this prompts the verifier to add a coin to the bank, and then the verifier just says, I just added a coin to the lot, to the prover. Now, so what the prover can do here is, because she has the ability to count and she knew how many coins were in the bank beforehand, she can count the coins that are currently present in the bank to tell the verifier if he was telling the truth or not. So in that way, the verifier can know if the prover really has the knowledge of the number of coins in the piggy bank or not. So that's what it does. That's a weird animation that I put there, but anyway. So the prover counts the number of coins in the piggy bank, and then the prover is like, because he got heads and he added a coin to the piggy bank, the prover counts it, and the prover in fact decides that the piggy bank now has one extra coin. She says that, okay, you're telling me the truth, you did add a coin to the lot. So then the verifier is like, yes, you're correct, but what if you just guessed that? Because there's only two outcomes to this. The prover can say you're telling the truth or you're lying, right? So what if she just guessed it, and what if she just tried to bluff, right? So the verifier then has to carry this on again enough times for it to be satisfied with the fact that the prover has or doesn't have proof of how many coins are in the piggy bank. So this interaction keeps happening, and it has to happen in polynomial time for the verifier to ensure or to believe the prover at the end. So this is what happened. For the proof to be accepted, the verifier should be convinced in polynomial time that the prover indeed knows how many coins are in the bank. But also notice that at the end of all of this interaction, if the verifier accepts or rejects, but he never really knows how many coins there actually are in the bank, right? He never counts them. So that's how you preserve zero knowledge in a very simple way. There's so many other parameters in real world, but this is a very simple way that you can use to understand the zero knowledge proofs. Right. So what do we learn from the example is that for a true statement and for any verifier, what a verifier computes after an interaction is essentially the same, is essentially equal to what the verifier should be able to compute before, which means that through the interaction, the verifier will not know any new details, right? So the prover does not give him, the proof should not be in such a way that the verifier gets to know any new details about the proof or the knowledge of whatever they're proving. So this is a definition that I just wrote, but I don't know if we can definitely go through completeness and soundness. It is to say that so these are the interactions. So A1 is the answer, Q1 is the question, and there's a claim X. So it's between the prover and the verifier. And there are repeated interactions. There are probably more, of course. It can't just be done in just two questions and answers. But let me check good time. Okay. So the definition says the prover and verifier is an interactive proof of L if V is a probabilistic polynomial x time. And there is completeness, which means that if the claim is in the language, then V always accepts. So that's how you ensure completeness of the protocol. And there is soundness, which is to say that if the claim is not present in the language, then no matter how hard the prover tries to convince the verifier will not accept the proof, and except with some negligible property that real-world computer systems don't really care about. So we can move on quickly because we have a short time. As a recap, the proof needs to be short. The proof consists of a secret witness, and the verifier the verification must be done in polynomial time, and the prover should not learn anything new after their interaction. Right. So these ZKB proofs of knowledge can also be translated into ZK snarks. So now that you've seen interactions, you should also know that in real-world systems we actually use non-interactive zero-knowledge proofs, which are called ZK snarks. This is important because we want the verification time and the proof time to be really short for it to work in actual blockchain systems. So yeah, when last week, I don't know when he was here, but I think that the beginning of the month when Vitalik was here, and I believe it was co-hosted by blockchain, Portalu blockchain, but yeah, he did talk about ZK snarks and how everyone should learn them because they're amazing. So I don't know if that's not good motivation, so I don't know what is. Okay, so what is a snark? Snark is a succinct proof that a statement is true. When you say succinct, it means short, very short, right? So, for example, there's this claim that I know a message M where SHA-256 of M is 0. So that's a claim that the prover has. And a snark would make the proof for this very short and fast, right? And very importantly, it should also be non-interactive for it to be fast. A ZK snark on top of the snark is something that preserves zero knowledge. So the proof is short, fast to verify, and also reveals nothing about the message M, right? So once again, I think the construction of ZK snarks, as much as I would love to talk about, are beyond the scope because it just involves too many mathematical parameters that will take a lot of time for me to explain. So I hope this definition is okay, and we can move on to know more about snarks in the real world for now. Okay. So the application of snarks in blockchain. These applications are not necessarily zero knowledge, but the important property of the fact that they need to be non-interactive is what is the main incentive of both of these solutions. But of course, like ZK rollups, they do use zero knowledge, but we can also look at what they are. So ZK rollups are basically a batch of multiple transactions off chain, and then roll them up into a single transaction. So the transactions actually happen off the chain, and then you roll them up into one roll up, and then you try to make a summary of it, I think, and then you put it on the blockchain. And so whoever tries to check the blockchain transactions learns nothing about the transactions themselves, but just gets access to the summary that was presented. And ZK Bridge is a proof of consensus, which is it facilitates the transfer of assets between two blockchains without actually revealing the contents of one blockchain to the other. So you can it's a pretty interesting, I think, example of using ZK snarks in blockchains. So you can read more about that in your own time. And applications of ZK snarks in blockchain are for private transactions. So basically everything that a blockchain can do, but with privacy and anonymity of the user, right? And the example for that is Zcash, which we will talk about in a bit. And there's also compliance, which says to make technology compliance with policies, it is possible to use ZK snarks, right, to verify if at a given time a certain protocol complies with necessary policies. And I know for a fact that there are some really nice implementations of this, but they're probably not in blockchain, so I did not present them here right now, but Espresso is a company that does this. So how much time do I have? Okay, thanks. I'll just quickly go over Zcash and then we can wrap it up. To quickly recap of what a blockchain transaction change actually looks like. For example, there is an input of 5 Bitcoin from Alice, and this transaction is between Alice and Bob, right? So 5 Bitcoin from Alice is inputted and the output is 30. So we're trying to transfer 30 Bitcoin, and there is a change of 20 that is sent back to Alice's address. So the way that this is done is obviously through addresses. I hope you're familiar with addresses and how linkage happens. And this transaction is signed by Alice, which means that Bob has to verify it and to know the authenticity of the transaction. And then this is linked to another input of 30 blockchain from Bob, and the output it goes to a Carol, 15 bitcoins, not really important, and it's signed by Bob. But what I wanted to show here is the fact that it is possible to retrace, I don't know how I would call that, but to go back in the link and to check where these blockchains are really coming from with the help of the addresses that are provided, right, for Bob or Carol or Alice. So it is possible from here to trace back to Alice, is what I think, is what I understood from Bitcoin transaction chain, right? So the problem with this, I just said that, it's easy to backtrace to the owner. So Zcash is actually a fork of Bitcoin with optional anonymity features, which means it does support transparent blockchains, but it also has some anonymous features that users can decide to use. What it does is, it is aimed at delinking senders and receivers in a transaction. So as with blockchain, Zcash coins are sent to addresses, and they can be thought of as public keys. So only the owner corresponding to the private key can generate a new transaction. So there is user anonymity in Zcash established that way. To get into this a little more, so there are two classes of addresses. One is permanent and the other is shielded. So transparent and the other is shielded, sorry. So the transparent is equal to whatever happens on the regular blockchain, but the shielded transactions are what happens between two Z addresses, which is to say that they are not, the transactions that happen between these two addresses are not open to the not openly available to the public, and that is done through zero-knowledge proofs. Right. Okay. So a Zcash transaction, as in contrary to what we previously saw, is something that looks like this. So there is 50 ZCs, I think. Yeah, first the coin is. It goes from the Alice's T address. T address is the transparent address, and the output is 30 to Bob's T address, which is also transparent. So this is signed by Alice, but for a private transaction, it goes from Alice's T address, transparent address, to Carol's Z address. And because this goes to a Z address, the whole transaction is a zk-SNARK proof, which is signed by Bob. So this transaction essentially is not open to anyone who has access to the blockchain, so you can't really see it. That's what Zcash does. And the limitation with that is obviously the fact that there would be high computational costs of shielded transactions, because it takes way longer. It takes like between 30 seconds to 1 minute for one transaction of a shielded nature to occur, and this obviously makes users really impatient and just want to do the transparent transactions. And the linkability of round-trip transactions, which means so a pattern of transactions where coins are sent from a transparent address to a shielded address back to a transparent address, often with the same amount. So it is possible to actually look at access patterns in this way for transactions to link it to, even though they're shielded, it is possible to still link these transactions to transparent ones, right? So a paper that is linked here has actually identified that 31% of all coins that are on Zcash are of this nature. So, and the third thing is that most cryptocurrency exchanges that trade Zcash only accept transparent addresses. Okay. So, now that we saw what Zcash is, we could quickly review what the current research in the area is. So these are a couple of zk-SNARKs in the industry right now. There are research that's been going on for years. So the Groth16 is super popular, I think, and as you can see, there's length of proof and verification time and whether or not it's post-quantum secure. if you see here that if it's not post-quantum secure, the initial groth16 was really fast, length of proof was very short, and the verification time was really fast. And same for Planck. But Stark here was really is really important addition to the ZK SNARK research, like digital signature, because Stark is post-quantum secure, first of all, but although it had really high verification time, it's doing, I think there is a Starkware is the name of the company that uses Stark, and it's quite in the race of being like a very fast and affordable solution to using ZK SNARKs on blockchain. And there's also Aurora, Prion, and Polaris is something in-house. So, it's something that our lab is working with. I did not work on the algorithm, but I am trying to help implement it with Taghi. So right now, our length of proof is 2 and 4 kilobytes, and it's also the verification time that's projected takes 13 milliseconds, but it's probably more than that. Hopefully I can fix that, but that's about Polaris. And as you can see, the length of the proofs and the verification times are quite large for ZK SNARKs for now, right, as compared to traditional blockchains. And it is safe to say that the scope of improvement is vast. And currently we're also implementing other post-quantum cryptographic algorithms on the blockchain. That's what the research that's going on. And there's also optimization techniques to improve prover and verification times, and there's a faster implementation of ZK signatures. Hash-based ones are concerningly slow, and using GPUs to accelerate polynomial commitments and intermediary computation essential for ZK SNARKs is something that I'm working with right now, is another research area that's in ZK SNARK. So here are some ZK research readings. If you wish to, the MOOC that is taught by professors from MIT, Berkeley, and Stanford. I think if you're able to share these slides, you would find that the link is here. It's actually it's embedded. You can go over these blogs, and I would also really recommend you to, if you're not already into it, you should definitely look at number theory and algebra, because I don't come from a math background, and I've been doing a lot of that. So it's really helpful. And there's also ZK Learning, which is essentially the same MOOC, but it's like a course that I think that you can do. And their Stockware is just something that I was talking about. They have really good blogs about different protocols that they're using in their ZK SNARK implementations. Right, so that's all we talked about. We have ZKPs, and we introduced what SNARKs are, and Zcash, and ZK SNARK implementations and future scope. I do have, I was recommended to prompt some questions, but before that we can, if you have any general questions, I can try to take them. Yes?
Your table that you put, what are the sizes of the circuits that you're using? Because to me, these times are arbitrary. I don't know how big the circuit is.
Oh yeah, so usually the circuit size, for example, for Stark is 2 to 50, I think. Yeah, it's like, their biggest, the 50. It's like their. The Aurora, I would really have to check, but for Polaris, we're trying to make the circuit size to 192, right? Yeah, sorry, but that's something that's in their papers. I just noted down the verification time, but they're pretty big circuits, which is why the verification time usually takes a long time. But it starts with 2 to 15. That's how they, the smallest circuit, I think, is 2 to 15.
And when you say 2 to 15, you mean you're talking about a long visualization like rows?
Yeah, the rows and columns, and the output is 2 to 15.
Sure.
Yes. Anyone else? If there are no other questions, I do have a couple here, but we don't have to waste a lot of time in this. I do want to talk about this one question, though. So at the beginning, we saw a user linkability problem where we were talking about a healthcare system, and Can you think of a way in which ZK snarks can solve the problem? There are many solutions, but can you think of a ZK snark solution to the problem? Potentially. Oh, yeah. Yes.
Maybe redefine the user linkability problem.
Oh yeah. 1 second. I wrote very smart of me, but yeah. So is there a way that an adversary cannot link Alice's date to the date of admission, or try to narrow down the information to linking towards Alex? So is there a way that an adversary can do that cannot do that if you use ZK snarks? That was I used a link here. Oh yeah. I'm pretty sure you would have got it, but it's just that it's instead of publishing patient data on the blockchain, so transactions can be computed off the chain, right? So just like how we discussed ZK rollups, you can do that, and then after a whole bunch of these are computed off chain, we can summarize them and present a zero knowledge proof of such a summary to the blockchain. So when the adversary actually looks at the transaction on the blockchain, he would not be able to link it back to Alice as we saw previously. So, yes.
I'm not sure, like, if I understand correctly, but like, what exactly is was the original goal of posting the data on chain to like verify some type of eligibility of the patient, or what was the
well, when I say posted on the blockchain, I just mean that if every transaction has a node that contains information of the owner of the owner of the transaction that actually published it. So when you try to look at that scenario from a hospital database, so for it's different probably for financial systems, but in a hospital database, the data that is published on a blockchain could actually be linked or information related to the medical stuff that the patient has, right? So if all their database is on the blockchain, then obviously all the information that is published is probably important stuff that's related to medicals. Maybe doctors are using it, maybe other technicians might have access to it to quickly check the file or something. So the database itself is blockchain, then we could try, there is a possibility of having it linked to the patient itself. So when it's published, actually the name and other PII is actually hidden in some way, but it is possible that through other means that the adversary can actually get individual data from this transaction. That's what I mean. I don't know if that answers your question.
I mean, I was more thinking about like the purpose of proof here. I don't know if I'm
Oh, proof. Oh, sorry. Okay, yeah. So what I mean is, instead of putting each transaction of every patient directly on the blockchain, so what happens in ZK rollup is you compute the transaction off the chain, which means you do it in a separate database, and then you try to put that into a zero knowledge proof and put the proof onto the blockchain, so that whoever has access to the blockchain is able to verify the proof to see that it is actually authentic to where it comes from. And then instead of having the actual data, so when the proof is there, you don't really learn about who computed the proof, right? You don't learn about through ZK snarks, you don't learn about the patient. That's what I mean. Right. So that's all I had for today. Thank you.
All right, while we get ready for the next speaker, if you guys want to grab some of the pizza we have here, feel free to come down and grab it, and then just give us 3 minutes before our next speaker. Thank you so much.
Can you disconnect the...
What's up?
I was thinking.
You want the live chat, right?
Hopefully we don't. We can share this screen, right? Customization.
Mm-hmm.
What the? Why?
I think we'd have to restart the whole
We're trying
stream.
to enable live chat for the stream. But I don't know.
You know what? I
how
think
are you?
it's too late, to be honest. Hey everybody.
Oh, yeah, it's still streaming.
I guess we'll just have to deal with
Yeah,
that
it's-
as at a
It's
separate.
fine, I guess.
We'll figure it out for next one. That's fine.
Guys, you can, if you're in the stream, you can ask questions on the Discord server.
Hmm?
You can
Oh,
ask
yeah,
questions
yeah.
on the Discord server.
Discord. All right, this is the next one. Taji's going next.
You're going next, right?
Oh, okay. Did you shared it with me?
Yeah, I shared
Okay, awesome. Just give me 1 sec. All right, you guys get to all see my emails. That's awesome.
Amazing.
Can we make the speakers, video webcam
Bigger, smaller.
Smaller. It was,
Sure.
it was covering some of the text,
we
so
can,
yeah.
We can.
All right, let's just let's get that figured
Okay.
out. How do you make it smaller?
No,
That's not what I want.
just double click on that. Yeah.
Oh, I see.
Yeah. Hmm. Oh.
Fair enough. I'll send it wrong. What are we scheduled? I thought that's lunch open stuff. That's why this. Probably. That or like that. Fair enough.
But like, yeah, just yeah. Are you ready? But I want to do it. I might do it like. Is that from Zach or?
No, it was actually just like I
thanks everyone. I hope that you enjoyed the first talk. Our second speaker is from industry, Marston. He's co-founder and CTO of JACKAL. So it's decentralized storage solution. So if you have heard like other solutions like Filecoin, so they're a new solution. And I think I first saw you in hackathon. That's you over as a sponsor. So they are doing really cool stuff. Actually, my presentation is kind of related to decentralized storage. So yeah, that's stuff. Yeah.
Cool. Thank you very much, everyone. Thank you, Waterloo Blockchain, for having me. My name is Marston Connell. As he said, I'm the co-founder and CTO of JACKAL Labs. We're a Canadian-based startup working on decentralized cloud storage. So to kind of start us off, what is cloud storage? You're probably used to cloud storage being kind of these more centralized entities. So, your AWS, your iCloud, Google Drive, the stuff that you're familiar with. And these cloud storage platforms, essentially all they do for you is hold your data off your computer, right? But there's a lot of problems with these cloud storage solutions. The big one, they're centralized. And what does this mean? It means that all of your data is on their systems and theirs alone. Being said, they can lock you out of your data anytime, just for no reason at all. If they deem what you're saying or like what you're storing to be against their terms of service, they can shut you out. They can delete your entire account. Your data can just go missing at the drop of a hat with really no recourse for you. On top of that, you gotta trust all these things, right? You upload your personal information, whether that be like important contracts, personal photos that you don't want anyone else to see. All of this stuff is going onto their systems fully open, unencrypted, which means that anyone that's has access to your data, like employees of these companies, they can just see your data. They can go in, they can mess with it, they can do whatever. So you have to really trust these companies that you're giving your data to. On top of that, kind of going back to that first point, they're not censorship resistant. So if you're, a journalist, let's say, and you're posting opinions on your home country that's a fascist government, if one of these cloud platforms are operating in that country, they can be subpoenaed, which means they can go in and they can take your data down because it's against what the government mandates. And the last thing that you're probably hearing a lot about is like data mining. So whether that be for advertising or more currently, artificial intelligence, all of these companies are taking your data and they're running their either AI models or advertising models on them and selling that, either the data itself or the models that they're generating through advertising or AI models. And you're basically just handing them all of your data for free. You're getting nothing out of it except a little bit of free storage. And that's kind of the thing, storage isn't free. Storage has to be stored somewhere. There's a lot of overhead. So anytime, that classic, if it's free, then you are the product, couldn't be more true with cloud storage. So what can we do about this, right? Well, decentralized platforms store your data better. And I say better because I mean better, not subjectively better. It stores your data in a way that is truly, truly yours. So, let's go over that word decentralized a little bit. What does that mean? Because is AWS decentralized because they have servers all over the world? Well, my definition of decentralized might be a little bit different from theirs, but I'm not talking about just geo-distribution. I'm talking about full, top to bottom, ownership of your data. There's no middleman involved. It's truly owned by no one. So decentralized storage platforms, they're like any other cloud storage. They have issues that arise, and in order to make them scalable and safe for you to use, we have a few things to overcome. And a lot of these decentralized storage platforms today are doing just that. So what are these pitfalls of decentralization? The big one, probably the most important one, is verifiability. If you're with AWS or with Google Cloud, you're giving your data over to AWS or Google Cloud. You know that your data is being stored with this one company, and you can kind of trust that they will hold onto your data because they have incentive to do so. They have a reputation to hold on to. In decentralized storage, anybody can provide storage. It doesn't matter. You don't know necessarily who's actually storing your data, and because of this, there needs to be ways for you to verify that they're actually holding onto your data. Because if I was to spin up a storage provider, offer my services to this decentralized storage network, I could say, hey, I'm storing your data, but in reality, I'm storing nothing, making money for doing no work. So we need a way to overcome this. Second really big issue is scalability. Decentralized platforms don't have the funding of a full integrated Web 2 company like Amazon. So, we're not able to control the machines that your storage is running on, right? So AWS can put top of the line data centers in. If you go to AWS and say, I need the best of the best, they will give you the best of the best because they can guarantee the best of the best. Decentralized platforms, again, because you don't know who you're dealing with, you can't verify any of this. So scalability becomes a real challenge because you need to put incentives in place to do better. And the last, still very important thing is insurance. So much like verifiability was assurance, insurance is really important because what happens if your data disappears? And it inevitably will. A hard drive doesn't last forever. So, in traditional Web 2 platforms, you've got like backups. If you go to Amazon and their server fails, well, they have 2 more servers backing up everything, right? You can kind of guarantee that if your data goes away, either it's backed up or you can sue Amazon because you've made a service level agreement with them and you know who you're dealing with. But again, decentralized platforms, you don't. So let's start with verifiability. If we don't know who's storing the data, how do we make sure it's still there? And that is probably the most important thing to overcome with decentralized storage. And the answer is Merkle trees. So we're going to talk a little bit about what a Merkle tree is and kind of how they work and how they relate to cloud storage. So this is a diagram of a Merkle tree, right? So at the bottom there, that is our file. When you want to create a Merkle tree of a file, you split it into a bunch of little chunks. So you can imagine, if this file is 8 kilobytes, each one of those little chunks at the bottom is 1 kilobyte. I've lettered them here so that we can, refer to them. But essentially what a Merkle tree is it uses a hashing algorithm. So it takes 2 nodes at the bottom, hashes them together, and creates a new node. And then it does the same for all of the nodes. It then has, a new layer above it, and then we hash those together. And we hash them all the way up in pairs until we hit the very top, which we call the root. So if you kind of picture it, if you flip it upside down, it looks a lot like a tree, with all of those pieces of the file being the leaves. If we want to go ahead and say, I want to prove that this piece D belongs in this file, right? Because that's really cool. If we can just take a singular piece of this file and prove that it belongs, well, we can start to work on that verifiability problem. So if we take D, we can build a proof structure, which, because of the way the Merkle tree is built, only requires C, I, N, and the original piece D to be kind of packaged together into a proof, and then we can use the root to verify that it's there, because we can rebuild the tree from just those pieces. So this is kind of what JACKAL does here. We take that same approach, but we need ways to kind of manage which pieces we're looking at, right? Because we don't want them to just be able to prove the starting piece over and over and over again, because then they only need to hold on to the starting piece. We want them to hold on to the whole file all the time. So our approach is we use random sampling. Over the life cycle of a file, what we can do is if we randomly select these pieces, the storage provider that's holding onto this file won't know what piece needs to come next. And if we sample enough of those pieces, they will need to eventually hold on to all of those pieces and prove all of those pieces at some time, and they won't know the order. So at that point, it becomes more work for them to offload the pieces that they're not proving and then pull them back when they do need to prove them, because they never know what piece is coming next. On top of that, we now need to index these pieces, because a Merkle proof with the root can be valid. If I give it piece A, even though they're asking for piece D, unless I have a way to prove that I'm giving them piece D, the blockchain that's verifying these proofs won't understand that it's an incorrect proof. It'll still verify it. So what we do is we index all of them. And then we hash piece A with index 0, piece B with index 1, piece C with index 2, and so on. And this creates basically an entire new tree. If you chop off that whole bottom, that's your standard Merkle tree. So what we do now is, because we have all those new pieces, right? You're thinking, well, if I can just use those pieces to prove the Merkle tree, what's the point in me even storing the files originally? Why can't I just store the hashes, right? This is where the blockchain comes in, and the blockchain enforces a very specific set of rules. So this is kind of an example of that blockchain data. So this is what a file looks like on the JACKAL protocol metadata-wise, right? So we've got the Merkle hash, which is that big long string of characters up there, and that's the root that I've been talking about this whole time. And then we also have these proof objects, which these two are examples of proof objects. Those are identifiers. And then we carry them over to this, and you can see that data matches right there. That Merkle's the same, and we ask it, which chunk it wants to prove. And that data, that index for the chunk to prove, adjusts over time and is randomly selected out of how many chunks fit in that file. So if we want to choose, we want to verify chunk 1, right? That's B, right? So from here, we don't just send J, because that's where the Merkle tree starts and everything, and that's all well and good. But if we send that to the blockchain's rule set won't allow that. What the blockchain does behind the scenes is every time you send up piece B, it's going to know, because it has it on that blockchain, that we're looking for index 1. It's going to then take B that you've sent it, hash it together with index 1, and then start the process from there. So you do need to actually send it this bottom layer, because it creates that secondary layer on the fly as it's verifying. And same thing goes, we can send it B, we can send it I, we don't need to send it A, because that's not what we're proving right now. And then we can just send it all of those other pieces, it rebuilds the whole root, and then we can verify that B was indeed a piece of that file. So that kind of covers like how we verify that data. We randomly sample that data over and over and over again, and eventually we can prove that that file's there. What's the point, right? Why do we even prove it in the first place? Well, that's another really great spot where the blockchains thrive. It's where blockchains really excel at this, and it's the token layer built into the blockchain. So what we can do is we can create these deals on chain that you just saw, and we can tell the storage providers that if they continue to prove those deals, we're going to pay them in tokens, right? So on the JACKAL protocol specifically, you hand the protocol your tokens. Those tokens then get put into a big account that keeps track of all of your payment information. And then as storage providers prove those files over and over and over and over again, they get drip fed those tokens. So the more files they're proving, the more money that they actually make from the protocol. So following up, scalability. Scalability is a huge, huge issue, especially in blockchains. And basically, the proofs are really big. If we're talking about a file that's those 8 kilobytes and we're using those chunks, we have to send up a whole kilobyte every time we want to do that proof. That sucks, because the proof, on top of that, depending on how big your file is, the proof scales with the size of the file, and you're sending that original piece as well. So blockchains have limited bandwidth, right? There's a maximum amount of block size, and you don't want to be filling that with that file piece that's going to be proven over and over again when you might not need to. So, we can take a look at some existing solutions and kind of what's been, done. And if we look at something like Filecoin, they currently use ZK proofs. So what that allows them to do is have a very small proof footprint, and they can prove very large chunk sizes without needing to do a lot more work and use up their bandwidth. Like on the JACKAL protocol, if we were to send a whole proof up and the proof chunk, right, was 10 kilobytes, you're sending a whole 10 kilobytes up. So that scales, and you can only fit so much on. The cons is if you're using really, really small chunks, a raw Merkle tree proof is generally going to be faster. Because it's all decentralized, you're doing the same ZK proof computations across every node in the network, which can get expensive. And on top of that, they still use a bit of bandwidth, right? They're still a proof that you're sending up and verifying. So although they're smaller, they still exist. We can look at off-chain verification as well, which is something kind of like what Storj does, where they're not doing that decentralized verification. They're looking at taking that data, storing it on a decentralized set of nodes, and then making sure that their central system is keeping track of who has what at what time. This is really fast, really, really, really fast. It has almost no overhead. As I say, it's not decentralized, so you don't need multiple nodes running the same thing. It can basically scale infinitely, and it can prove any size pretty much instantly because, again, they can scale their hardware with however much load they want. The big con, which makes it pretty much unusable for any truly decentralized platform, is it relies on trusting a third party, which that trust layer is what we're trying to get rid of, right? So we've done something a little different. we've created this solution that we call consensus spheres, and it's a really, really interesting way to kind of get around those two systems while almost combining them in this fun way. So, the blockchain is a consensus layer. It's a bunch of computers that are all agreeing, right? If we go ahead and every time we want to make a proof, one of the storage providers says, hey, I want to submit a proof, the chain, all of the nodes can come to agreement, they can create a small little list of other storage providers. This we call a sphere because it's just a group of storage providers that are going to talk to each other and verify that they are coming to consensus. So it's almost like, if you have a big ring diagram of the current validators on the network, it's creating little rings off of the big ring, which is really, really cool. So then from there, the storage provider, when they go to make that proof, they send the proof to the storage providers. So that proof never even makes it to chain. So this is kind of going back to that off-chain computation that we were talking about earlier, where they're sending their data to the storage providers that are part of that new sphere. And then those storage providers verify that proof themselves. And because these storage providers are generally doing less work because they're not managing the overhead of the actual blockchain itself, they can compute, they can verify these proofs a little bit faster. They won't be using up the bandwidth of the chain. And then from there, they all come to consensus, which is why we call them consensus spheres. So once that little group comes to consensus, they all send an attestation to the blockchain itself saying, hey, I verified the proof, you picked me, we all kind of agree. And what this does is it basically allows us to reduce the overhead of sending an entire proof to the network to just a simple one-liner message saying, I would like to create a proof. And then it's basically just 3 by default, or however many the chain actually chooses, Boolean true or false value saying yes or no, this proof is valid, which reduces the overhead by a lot. And on top of that, the system's really, really great because it can also run in parallel with just the traditional proof system. If the consensus spheres fail, we can always roll back to original proving mechanisms per file. So, if this isn't like the whole network shuts down, it's just basically if, your one proof, if for some reason all the storage providers that get picked go down that instant, you can always post the proof. And that's kind of where we might switch to ZK proofs as well to make those proofs even smaller. On top of that, because it's blockchain and we all love roll-ups and stuff lately, there's kind of another scaling solution that we can use, which are child chains, or I guess roll-ups. And what that means is, the core JACKAL blockchain will verify your proofs. It'll manage all your storage deals. But that main chain has limited bandwidth. So what we can do from there is just kind of horizontally scale them out. We can create more blockchains, which means more bandwidth. And then using zero-knowledge proofs for scalability, we can shove a whole lot of attestations from one of those child chains into a single transaction, verifying that everything was true. And on that main chain, we can delegate all the rewards to the storage providers, but that main blockchain doesn't need to handle all of the load. So our last kind of pillar there, insurance. So what happens when things fail? Because they're always going to fail. Everything in the computing world fails, right? Computers get old, hard disks fail, even solid state drives fail. What do you do about that, right? And I kind of mentioned that in Web 2, you can kind of sue the storage provider that you're currently using because you have service level agreements, or you can tarnish their reputation. But in Web 3, that's very, very difficult because you don't actually know who you're dealing with. So you can really do nothing. Most of the blockchains that exist today, Filecoin, Arweave, Siacoin, if your file disappears, it's gone. There's nothing you can do about it, which is really, really crazy when you kind of break it down. You're expected to go in and kind of create your own redundancy. So, if I want to upload my file, I upload it 10 times because I just am hoping that surely not all 10 storage providers are going to die before my file deal is expired. So, here at JACKAL, we said that's ridiculous, right? We want to service businesses. We want real people to be using cloud storage in a decentralized manner. And so we created 2 protocols that we built in, JPOP and IDLE, which stand for JACKAL Proof of Persistence and Internal Detection of Loss. And we're currently the only blockchain that actually does this in decentralized storage. And essentially what it does is the proof of persistence manages redundancy on the blockchain. So what that means is if you upload a file, we actually create 3 copies of that file, so that if a copy ever does go down, you have 2 more. And then storage providers, if there's only 2 copies on the network, they can go and they can claim that empty 3rd spot and remake that deal, download the file from the other 2 storage providers, and boot right back up to 3x redundancy. So you don't have to manage your redundancy at all. On top of that, you can choose your own redundancy. If you want to pay for more redundancy, you can pick 10 copies, you can pick 20 copies, and you can pick 1 if you're feeling really, really ballsy, you know? And then the internal detection of loss, that's kind of the way that JPOP manages to know when those files are down. Back to that verifiability, when those storage providers are making those proofs over and over and over again, the chain actually knows, hey, this storage deal hasn't had a proof submitted for like 12 hours. Probably means the storage provider is dead because it's supposed to be submitting those proofs. The blockchain knows this because it's, we use a Tendermint blockchain, so it's really, really fast. It can do a lot of computation in a really short amount of time compared to like old blockchains like Bitcoin or Filecoin. And from there, we can take that and we can actually tell the chain to kill that deal with the storage provider because clearly it's not doing its job. It's at that point that a new spot opens up and then the proof of persistence can take over and fill that spot. So, this is a fully decentralized, permissionless way for you to manage redundancy, for you to have insurance on your data, and to manage what is essentially a Web 2 way of dealing with backups in a Web 3 setting. So, yeah, I kind of talked about this, but decentralized storage is maturing. It's never really had redundancy, and so JACKAL creates that same file over and over and over again, and JPOP and idle manage everything for you. So, kind of circling back around, decentralized storage is getting a lot better. I've been talking about Filecoin, Arweave, Siacoin, and how none of these platforms have any sort of redundancy or insurance at all. And they're only, Filecoin's only 7 years old. It started in 2017, so it was basically a toy when it launched. It wasn't really, it was kind of a research project that wasn't expected to hit mainstream adoption. And so this is why JACKAL, we've positioned ourselves as a platform that's modular and expandable because we want to take what companies like Filecoin and Siacoin have been doing in the research space and bringing it to life that can service everyday regular people. So, we only have 5 years difference between us and Filecoin. And when you think about what 5 years actually means, that is not a long time at all, especially in computing. Stuff happens so quickly, but in such strange amounts of time. And we're really, really close to making that Web 3 data storage feel like Web 2 data storage. Creating those developer libraries to make integrating with AWS systems really, really easy. Or even just having a photo backup on your phone. It's not possible with Filecoin or any of these other decentralized platforms. It's becoming more of a reality with these kind of modular chains like JACKAL. So what is the future of decentralized data? It's having that full self-custody. It's being in control of your data. It's decentralizing as many of the working parts in a cloud storage network so that you know that your data is only being seen by you, it's only being accessed by you, it's only being controlled by you, and it can only be deleted by you. On top of that, we're talking a lot about interoperability. So, you're talking about blockchains interacting with each other, but more importantly, blockchains interacting with other services, like existing Web 2 solutions. Not everything needs to be a blockchain, and so we need to interact with non-blockchain platforms. And so we're starting to see a big shift into kind of these Web 2 platforms, integrating Web 3 systems, and making sure that your data is yours even on those systems. On top of that, when we're talking about interoperability, if we have kind of a great example is the medical field. If you have medical records that you want, you got to go and you got to call your doctor and say, I want these medical records transferred to my new doctor, right? That sucks because that means your doctor has full access to them. And although it's against the law, in theory, they could just go and shred all your documents and you wouldn't have them anymore. What decentralized storage allows you to do is it allows you to take that data, make it fully private and secure, share it with your doctor, And if at any point you want to revoke access and switch to a new doctor, they can update your data, and then the second that you want to switch, you block them out, you move your data over because it's all yours, which kind of goes back into that self-custody. On top of that is privacy. Going back to it, I haven't really touched on it, but JACKAL's currently the only decentralized storage platform that has built-in privacy, which is pretty crazy to think about. You're uploading stuff to like Filecoin or Arweave. That's public for everyone. Somebody can just scan that network, and if you're uploading, a service agreement with somebody, photos of yourself that you don't want anyone else to see, you can't use any decentralized storage platforms except for JACKAL today, and that's getting a lot better through JACKAL and kind of making it easier for you to have that privacy and integrate sharing of files and everything, and make it feel very much like a traditional Web 2 company where you have those like sharing abilities. And then on top of that, decentralized storage right now is kind of slow, compared to Web 2, because again, it has to come to consensus. It's dealing with blockchains. We all kind of know how slow blockchains are today. Decentralized storage can only get faster. Consensus networks are going to get better. They're going to get faster. Hard drives are going to get faster. You're going to parallel compute a lot more, making things much easier for you, the end user. And then lastly is better portability. So, creating better standards for decentralized data so that you can use your decentralized data in more places. If you're, playing like a video game and you've got assets in your one game, you can kind of bring them over because they're all the same standards. And so creating those standards, creating that better portability experience for you bringing your data places is really big on the to-do list of future decentralized data endeavors. So that's it for me. Really appreciate you guys coming out. As I said, we're JACKAL, we're a decentralized cloud storage company, and if you want to reach out, that's my email, that's our website, and that's our Twitter. So yeah, thank you. Oh, I guess, does anybody have any questions? Yeah.
So in the case of that third file, let's say that gets like corrupted, or sorry, like the data provider doesn't exist anymore.
Yep.
Is there any additional cost to creating that new third file, and if so, who bears that cost?
It's kind of a strange thing. It's very hard to quantify that cost. It basically comes down to like the ingress and egress charges of whatever storage provider is currently running. So there's that bandwidth concern. But right now that cost is eaten by the storage providers. So we can't quantify that very much. But because the network knows like who needs what at what time, you can make it so that storage providers can only give up their data to other storage providers, like if it's being requested by the chain, so that prevents things like DDoS or spamming or anything like that, which reduces the cost to protect that data quite a lot. Yeah.
If I understood correctly, in case of data loss, we cannot do anything. Isn't it a very big problem for them?
Yeah, and that's kind of what we're trying to fix. Is if on the JACKAL protocol we have that kind of proof of persistence and internal detection of loss system, and existing systems don't have any sort of redundancy or any backups. So if your data does go down with them, you're going to find that your data is just kind of gone forever, which again really, really sucks, and it is that big problem. But with JACKAL and kind of these Web 2 companies, which is what we're trying to move away from, we keep redundancy, we keep multiple copies of the data. So if for some reason one of the storage providers does go down, it's able to be regenerated on a new machine somewhere, and your data won't be gone unless for some reason all three of those systems that are spread across the world go down within like the same couple hours of time. Cool, thank you.
I'll introduce. Yeah.
Was you doing it?
Yeah, you can do it.
Okay. Well, I mean, don't wanna.
Maybe.
many people left? You can start.
Okay. Allow me to introduce you to Taghi. So he's a PhD candidate here at Waterloo in ECE in the same lab as myself. And Taghi's actually pretty nice. All of the zero knowledge that I have started off with Taghi pointing me out to resources. And he does very cool stuff. He has a lot of experience with blockchain. He's working with supply chain stuff with zero knowledge and everything. He also works with a lot of protocols. I think he does a lot of math and computer science, which is very impressive. So he's here to present his one of his thesis.
Yeah, one of the papers.
Yeah, but it's mostly about supply chain using zero knowledge. So
Yeah.
have fun. Thank you.
Okay. Yeah. Thank you, Tanmayi. Thanks everyone for coming to this research circle. This is the last talk, and today, I'm going to complete the no one can complete anything, but I just want to wrap two previous presentation. One was on zero knowledge proofs and privacy. The other one was on decentralized storage. And I want to present a scheme on how can we have decentralized, anonymous, authenticated data storage. So why authenticated data record is essential? So you cannot write on a piece of paper that you got your degree from the University of Waterloo and go to a company and get enrolled. No one can accept that. So we want your certificate be authenticated. So that's why we need authentication. The first example is supply chain. Have you seen the movie Blood Diamond? DiCaprio had played in that movie. So the movie shows the labor in Africa for extracting diamonds. So that's essential that we have authenticated records of product, that it has ethical sourcing. We need authenticated records for other things as well, like temperature of a milk, that it's not beyond a specific temperature. We also need for clinical data. For example, you get your prescription from your doctor, you go to pharmacy, and the pharmacist need to verify that this is a valid prescription. And the last one is version control system. So like Git, we highly rely on libraries in our computer. We download them from Git, and if it's malicious, it's really big problem. And we had those attacks that people just made changes to those data, those codes, and no one checks, and so you install some malicious library on your computer. So we need to authenticate those data. But how do we verify the authentication? So if you have a data record like prescription, product status in supply chain, or Git commitment, the authentication can be a signature, digital signature, stamp, or seal. And the verifier can be like pharmacy, or for legalization, or companies that they verify that the data is authenticated. So the existing centralized solutions are password authentication. Like you log in your, for example, Dropbox. It shows that it's centralized. It has a centralized manager. It proves that you have uploaded that data. So one centralized server decide to do that. Digital signatures and certificate authorities is like, for example, you have a certificate authority. They authorize that this is your public key, and then you digital sign that data record, and everyone can verify that you had signed that data record. But what about decentralized solution? We can store on-chain if we have, for example, our Ethereum address verified by a CA. We can store on-chain, but it's really expensive. Still, we can sign our message with Ethereum address, Ethereum private key, off-chain. And we can actually pass NFTs to give authority to a party to sign a data. So, sorry, like this. We can use sign in with Ethereum. We use Ethereum private key to sign a data, and an NFT can show that you have the authority to upload the data. So a verifier I will show you in a scenario how a verifier can verify that you have signed that data. So let's show a scenario in supply chain. Romeo is he owns a warehouse and he wants to participate in supply chain. He wants to store milk. So it is fully decentralized approach. So we have no centralized party. Romeo has to ask for a token from the previous person in the supply chain, which is Juliet. Juliet passed the NFT to Romeo. Romeo signed the milk history with his Ethereum address and store the data on decentralized cloud storage. That can be JACKAL or IPFS. Auditors then see the data and check the blockchain. So if the address that Romeo used for signing the data has the NFT, so Romeo is a valid user for signing that data. So what are the benefits of the decentralized solution? It's more agile. So in centralized solution for supply chain, there should be a centralized server. They should decide. And for fast modifications in the supply chain, for example, during COVID, we had to modify our supply chain. We had a big problem in the supply chain during COVID because we had some flights canceled. We had some flights that they were empty, so we could not use all the resources because our supply chains were old. We could not agilely modify the supply chain. And actually, we can add or remove different entities to the supply chain. Walmart could reduce the time needed for analyzing Mongos from 7 days to 2.2 seconds using Hyperledger Fabric. Hyperledger Fabric is a permissioned blockchain. Do you know what permissioned blockchains are? Are like a blockchain that you can set it up, but for example, we are in the class, we can set up a blockchain ourselves. We don't 100% trust each other, but we don't want anyone else to join this blockchain. So it's called permissioned. We don't trust each other, but only us should be in the blockchain, sorry. And we can achieve trustless automation. Smart contracts provide trustless automation. And it gives the chance to non-reputed entities, for example, small companies, like, for example, if you have an Instagram account for shopping your goods. So, for example, Walmart won't participate with you to let you connect to the supply chain. So you should have to 100% rely on Amazon or other companies. Otherwise, you don't have access to any supply chain. But on a decentralized solution, I mean fully permissionless decentralized solution. So you can just quickly join a smart contract and start the contribution. And so permission blockchain. I mentioned you that Walmart uses permission blockchain. It's a good solution for big companies, but it does not support fast changes because each small company has to rely on the, for example, protocols provided by Walmart. And requires small entities to rely on big companies. And also, it has high cost of developed solutions. So either you have to implement the solution yourself, or you can use the existing solutions like IBM Supply Chain Essential. It's $2,000 per month for up to 5 supply chain partners. So it's really expensive. So permissionless or public blockchains like Ethereum. They're fully decentralized, so they're secure. They enable global contributions. They are also good for small companies. They can quickly join to the whole ecosystem, and they're transparent. But they have really high cost of on-chain storage. So we cannot store the product history on chain. We have to look for some cheaper solutions. And they're too transparent. People that they are involved in the business, they don't like that level of transparency. For example, all people can learn which entities are collaborating with each other. and the history of interactions and how much money an entity has. So it doesn't make sense for many business partners to collaborate on those public blockchains. So let me show why we don't assume any anonymity in Ethereum. Romo wants to buy some ETH. It needs that to pay gas for at least transferring tokens. So he has to get that ETH from an exchange, and that exchange has KYC. And so the exchange at least knows that this Ethereum wallet is connected to that identity. And also, using graph analysis, many other people can also learn, find the connections between the nodes and can learn that this Ethereum wallet is connected to the identity of Romo. So why do we need anonymity? In supply chain, I told you that business owners, they don't like to share their secrets. Clinical data, I think it's clear. No one likes to share his or her prescriptions on the internet and the connections between the entities. If you get a prescription from for example, heart doctor, so everyone can learn that they either they cannot read the prescription, but they know that you have connection with that doctor, so you have heart problem. And version control system. Sometimes some developers, they want to be anonymous, like Tornado Cash, like solutions, or some other solutions that we have, like Satoshi. He wanted to be anonymous, and if you want to rely on those solutions, he wants to stay anonymous. So today I want to quickly introduce our paper that the preprint is available through this QR code. It's anonymously maintained decentralized DAG data record over public blockchains. So here are entities in the supply chain, and they upload their data records in any storage. It can be IPFS or JACKAL. And they use blockchain for transferring some anonymous tokens. So anyone who has a token can upload data to the storage, and they can pass that token to the next entity. We need DAG data structure because we have that data structure in supply chains. We have ingredients that they combine, or one material that can be used for different supply chains. So we need DAG data structure. DAG is directed acyclic graph. It's like a graph that doesn't have any circle, but they can merge, they can divide. So that's the good data structure for supply chain. The abstract architecture is entities that they are provers. They want to prove that they have a token. We are using zero knowledge proofs. They want to init a token. It's like minting a token. They want to transfer. They want to merge or divide. And also they want to upload data to decentralized cloud storage using those tokens, but they want to stay anonymous. And we have some auditors that they want to audit those data. So those decentralized cloud storage, they don't have any code running on them. Everything on that, you cannot ask, for example, JACKAL to verify my data. So they just store your data. Maybe in future they add that option as well, but for now they don't have that. So auditor has to verify the proofs. It should be easy for everyone to verify that proofs. So the non-fungible tokens, we assign each token to an entity, but for anonymous authentication tokens are stored in a pool. We have a pool of tokens, and owners are visible in NFT, but owners are anonymous. And there is visible link between sender and receiver of tokens, but we should hide that link in anonymous authentication token. An entity should be able to prove a proof that it owns a token or tokens in the pool. So this is the scheme of the token. Q is the quantity of product. We can modify that for different applications. PKSig is a public key that the entity uses that's corresponding secret key for signing the data. And rho is used for preventing a token from double spending, retransferring. So if a token is transferred, the sender has to publish the end of life number on blockchain. And commitment is hash function. So here we have two hash functions. So the token owner wants to mint the token. First decide on these values and then hash them and publish the commitment on the pool. So pool of anonymous authentication tokens means that the pool of these commitments. So how do we realize that pool? We use Merkle trees. So if, for example, we have a token in the orange box, it's not private yet. So the prover can provide those blue box to convince the verifier that the prover has a token in that pool. So now in this solution, the prover has to provide all those blue boxes that reveal the location of the orange box. But in our case, we don't want to reveal that which box here we are going to provide the proof that we own. So we want to hide that. So we implement that as a circuit in ZK Snark. So the public inputs to that circuit are on the root, and we have a proof. The proof that proves that I have an authentication token in that tree, and this is the root of the tree. So by having the root, the verifier is convinced that there is an authentication token that the prover has the pre-image of that. The pre-image, by the pre-image I mean these values. And these are hidden, so you don't reveal them. So we maintain the public input, I mean just the root, on a smart contract. So this is the actual more detailed architecture. So for the smart contract, we have public parameters that they are used for proof verification. Root, we need to store the root of the Merkle tree. We have to have the end of lives, so it prevents from double spending, retransferring. And also we need to verify each changes to the root. Before getting into that, let's see other entity and other parts of the architecture. So entity also have public parameters for providing for making the proofs. It is the set of our tokens. They're related to that entity. This is the Merkle hash tree, and the entity has these functions. Entity inits a token. So initting a token cannot be anonymous. So because you are going to do that with your Ethereum address. But when you transfer a token, we are going to hide that which token is transferred and who is the receiver of the token. We can merge, we can merge two tokens that we don't reveal which tokens are merged. So when we merge a token, the quantity are added together. And when we divide a token, each new tokens if you sum the quantities of the new tokens, it should be equal to the quantity of the first token. And it has two other functions, upload and audit. So they use this function for signing a data record, upload that anywhere in the DCS. The data record goes to the DCS, and also entities can audit each data record. And the DCS only store the data, nothing more. But how can we ensure that this new root, for example, if I send a transaction to the smart contract, and I claim that I added that commitment to the tree, and this is the updated root. How can the smart contract verify this is the correct root? So it's not just a garbage value. So we cannot store the whole Merkle tree on the smart contract because it's pretty big. So we need to find the algorithm for finding that. So for doing that, for initializing the Merkle tree, we assign indices to each leaf. And if someone adds a new commitment, for example, here into the ith leaf, they just send a proof, Merkle proof, for this index. So the smart contract maintains which index is not allocated. So the smart contract knows I. And this ith leaf is initialized with value I. So if in transaction they send the Merkle proof for this leaf with the value of I, they can get the previous root. And if they use exactly the same proof, but with the commitment there and updated root, so the smart contract can verify that this commitment has been added to that location of the Merkle tree. So it's not just a garbage value. So and it's hard to just forge those proofs because of collision resistance of hash functions. So, and this is the tag data. I mean, the data storage in supply. We use, because I was thinking about IPFS, we use addressing scheme in IPFS. That's no content identifier. It's just hash of the data. So we need to point to the previous data. We store the CID, the content identifier of the previous data. Each data has two parts, one public part that anyone that has access to the storage can see that, and it can have private part that is encrypted with a unique key. So the key can be, we can use different key management schemes, but it can be generated like forward secrecy scheme in Signal protocol that Mesh has used that, but it's you are open to use any other approaches. And these are tags. Tags are like if authentication token is changes during a data sequence, so the previous token owner should give the new token owner some tags. So I won't go into the details. And it comes with a zero knowledge proof. The zero knowledge proof is that I have an authentication token in the pool. This is a public input that can be the root. And here we have the public key for signing and sign the whole data for we use digital signature. And this is the proof that this root is stored on Ethereum blockchain. Any proof you can use, Merkle tree, depends on the blockchain that you are using. Actually, auditors can read the blockchain himself. So just to wrap it up, we could implement it, like practically. These are the costs. The baseline model is similar to NFT, not completely exact the same, but it's kind of similar. So for transferring the cost for our scheme is, for initializing is 8. For transferring is about $30. Actually, we assume that Ethereum value is 2,000. It's pretty old, so now it's higher. And for dividing, it's $33 US. So it's more expensive than the baseline model that does not provide privacy, but it is the cost that we pay for privacy. So to wrap it up, we have proposed authenticated off-chain data storage that anyone who reads the data can authenticate that this is a data that has been uploaded by an entity that got his authentication token from his previous entity. So it's verifiable. Also, it's anonymous and unlinkable. So no one can learn who is the uploader. The only thing that learn is that this is an authenticated, authorized entity. And unlinkable. So we have a pool of entities. No one can learn which entities are collaborating with each other. It can have broad applications like more than supply chain management, as I said, in version control systems, clinical data, and it's storage technology independent. So we do not rely on IPFS or JACKAL, but we are open to any decentralized or even centralized solution. Still, we don't reveal our identity. So we hope that it can be as a lower, because in public blockchains we have that idea of designing modular things. For example, when Vitalik proposed Ethereum, in his blog he wrote that the Ethereum can be underlying layer for many applications. And now we have layer 2s. We have decentralized storage. So we wish that our scheme can be an underlying layer for many applications that they need data storage, that they cannot store that on blockchain, and they want those storage to be authenticated. So still we are in the beginning, but I think we can just, we have a lot of things to do. So thanks for listening. If you want to still download the Zopla, you can use this QR code. If you have any questions, please ask. So, any question? Nothing? So if there is no question, I want to just thank everyone for joining us to this research circle. And you can access the talks, I think, on YouTube, yeah? Yeah, you can still see the talks on YouTube. And yeah, thanks for joining us.
great talk.
Oh, thanks.
Let's end it.